Hello, we're going to go over AP Chemistry, Chapter 4, Section 3 on limiting reactants, theoretical yield, and percent yield. So for a mixture containing 42.5 grams of magnesium and 33.8 grams of oxygen, what is the limiting reactant and the theoretical yield? So we need the balanced equation in order to do this because this is a stoichiometry problem. So we have our two magnesiums plus our oxygen is going to burn. This is the magnesium lab where it burns really, really bright. And we form 2 magnesium oxide, 2 moles of magnesium oxide. Okay, so put both of our givens over 1. Basically, we have 2 stoichiometry problems going on here. That's a G for grams. And so I'm going to go from grams of A to grams of B. So the whole value of the moles from grams of our given to grams of our product here, our given reactant to our product. So in order to convert from grams to grams, the first step is to divide by the molar mass. So I'm going to put the molar mass of magnesium down here. The molar mass of magnesium is 24.31 in 1 mole of magnesium. Okay, and then I'm going to change from moles, since grams have canceled, from moles of magnesium to my product that I'm trying to find. Whoops, I put that one a little prematurely. We'll come back to that. Moles of MgO go on top. Now, the actual numbers here, because this is our mole ratio, comes from the balanced equation. So what I should have put was 2 and 2, which is then going to cancel out. So we're okay there. All right, so now I have moles of magnesium oxide. I'm going to change it to grams of magnesium oxide by multiplying by the molar mass. So when we add our mass of magnesium and mass of oxygen, I get 40.31 grams. Okay, so mathematically multiply the 42.5 and the 40.31 and divide it by the mass of magnesium, and we get 70.5 grams of MgO. Okay, so how much magnesium oxide can I make from my given amount of oxygen? So we're going to go from grams of oxygen to the grams of magnesium oxide. So first step, get rid of grams of O2 and change it to moles. So that is going to be 16 times 2, which is 32. Okay, and now we have the ratio. This time it's moles of oxygen to moles of magnesium oxide. And the ratio here is actually 2 to 1. Okay, and last step, the molar mass doesn't change. So it's still 40.31 grams of magnesium oxide in 1 mole of magnesium oxide. Okay, and if we multiply the top, divide by the bottom, we get 85.2 grams of MgO. So which one is our limiting reactant? The smaller number tells you which reactant you will run out of. So once we've used up all of this magnesium, we've made 70.5 grams of magnesium oxide. That is all it can make, and the reaction stops. Okay, the magnesium stops burning, and all we have is the 70.5. So let's write magnesium is the limiting reactant. Okay, so then oxygen is in excess, and that's usually the case because there's plenty of oxygen in the air. We're not going to run out of it. Okay, but if it was in a sealed container, we could. And it says calculate the theoretical yield where we just did. So this 70.5 grams of MgO is the theoretical yield. Okay, theoretical, that is an E. So that's our theoretical yield. Okay, last part of this question says, suppose that the actual yield, so when you measured how much you got in the lab, was 55.9, what is the percent yield? So to find percent yield, you put the actual over the theoretical. I'm just going to abbreviate, and then multiply by 100. So that's going to give us the actual, what we actually found in real life was 55.9 grams. The theoretical was 70.5 grams times 100, and that is going to give us 79.3%. So we lost about 20%. 4.3. This can be found on page 149 of your textbook. We have ammonia being formed from 2 nitrogen monoxide, that's NO, and 5 hydrogen molecules. We're going to make 2 ammonia molecules and 2 water molecules over here. Okay, so notice I left off the state of matter. That's because we are not going to need them for our calculations here. All right, so we have 2 given values. We have our 86.3 grams of NO, so that's 1 given, and 25.6 grams of H2, that's 2 givens, and we're asked to find the limiting reactant. So we have 2 stoichiometry problems to do. We're going to change it from grams of NO to grams of our product, which we're worrying about the ammonia in this problem, because it says theoretical yield of NH3. And we're going to go from grams of hydrogen to grams of ammonia. Okay? So we always start by writing our given value, which is 86.3 grams of NO. We're going to put that over 1. And remember, in our valley of stoichiometry, we're going to go from grams of A to moles of A by dividing by the molar mass of A. Okay, we're dividing by the molar mass. So the molar mass of this is going to go down here. That means 1 mole of NO has a mass of, you add the N and the O together, nitrogen is 14.01, oxygen is 16, the total of the 2 is 30.01. That's how many grams you have per mole. Grams of NO will cancel out. So now I'm at moles of A, which A is just a generic term talking about our given, and our given is NO. So in this case, A is NO. We want to change it to moles of B, the one we're looking for. So we're looking for, if this is A, this is NH3 is our B. Okay? So we're going to go to moles of B using the mole ratio. And the mole ratio is the coefficient for each thing. So in this case, it's going to be a 2 to 2. Let's write that out. Moles of NO, because I wrote the unit and the molecule here, I know what needs to go on the bottom. Okay, so don't be lazy, write this out. And I know what goes on the top. It's the one we're looking for, NH3. Okay, so the ratio again is 2 to 2. 2 ammonias, 2 NOs, and now the moles of NO have canceled and we have successfully changed it to ammonia. But we have moles of ammonia, and what we are measuring in the lab, we'll see down here, is grams of ammonia. So I want grams of B. And to go from moles up to grams, we're going to multiply by the molar mass of B. Okay, that's a B. And over here, using our conversion factors, we can see we want moles of ammonia on the bottom. And what we're trying to find here is grams of ammonia. So this is, by definition, the molar mass. How many grams are in 1 mole? We have to add it up. 14.01 plus the 3 hydrogens, that's 3.03. We get 17.04. Okay, and then we just do the math of, these have canceled, 86.3 times 17.04, and we're going to divide that by 30.01, and we should get 49.0 grams of NH3. Running out of room there. Okay, so now that we did all that work, we get to do all the same work over again, but this time we're starting with our hydrogen. So we had 25.6. Let me erase that really quick. Okay, and let's see if my calculations are actually right, because I noticed that there's a wrong number over here. I don't know where that came from. So we have 25.6 grams of H2 over 1 we're going to divide by the molar mass of, now hydrogen is my A. So we're going to divide by 2.02 because every H2 has 2 hydrogens in it. That's how many grams are in 1 mole of H2. Okay, then we're going to use the mole ratio to change from moles of H2 to moles of NH3. Okay, and the ratio of hydrogen to ammonia, there are 5 hydrogens, so the 5 goes down here, and the 2 ammonias goes up there. And last but not least, moles of hydrogen have canceled. Mole of NH3, we already added the molar mass for that, it's 17.04 grams of NH3 per mole. Okay, and I'm going to use my calculator here to check my work. Okay, so I have 25.6 times 2 times 17.04. I'm going to hit equals and divide that by 2.02 and divide that again by 5. And I actually get 86.38, which would round to 86.4 grams of NH3. Okay, I see kind of why it didn't matter, because the second part, so we're going to find the limiting reactant, we're going to find the theoretical yield. The limiting reactant is the smaller answer. So once I've made 49 grams of ammonia, I will have used up all of the NO, and this will run out. So no matter what this was, as long as this number is greater, this didn't matter, but I got 86.38. This is the theoretical yield. That is theoretically how much ammonia we can make. So let's write that out. We would write the limiting reactant is NO, and the theoretical yield is how much we could make if we had used all of these 86.3 grams. Now remember, it's called theoretical because in the real world, not every single molecule of NO is going to turn into NH3, but if they all did, it would produce 49.0 grams of NH3. Okay, so this is my limiting reactant and my theoretical yield. The last thing it tells us to do down here, it says, suppose the actual yield was 55.9 grams. What is the percent yield? So the last part it wants us to calculate is the percent yield. So basically, how much did we get? Okay, and we got 55.9 grams of NH3. We were supposed to have gotten a maximum of 49.0 grams of NH3 times 100, and that is going to be 114%. So I wanted to show you guys a couple of things. Yes, you can have over 100% yield because we had more mass than we should have, and I wanted you guys to think about what that means. So is this a good thing if we are in a lab and we're starting with 86.3 grams of NO and I'm supposed to make 49, but I actually have 55.9 at the end? Not necessarily a good thing. Looking at the equation, what would be causing that extra mass? Can you guys think about what might be causing that extra mass that we measured, 55.9? If you said there might be some water contaminating the NH3 and you weren't purely measuring NH3, that's what I was thinking too. Or it could be some other contaminant in your container, which is also not a good thing to have. For practice 4.3 is from page 149. We have our reaction of hydrogen plus nitrogen making ammonia. And we have two given values. We have 5.22 kilograms of hydrogen. I'm going to go ahead and change that to grams right away. So remember that kilo means 1,000. So I have 5.22 thousand grams, or 5,220 grams of hydrogen, and 31.5 kilograms. 31, move the decimal 3 places to the right. 31,500 grams of nitrogen. Okay, and we want to know what is the theoretical yield. So we're going to change both of these from grams of our reactant to grams of our product. Okay, so to go from grams of A to grams of B, remember there are a few steps. First change to moles of A, and then mole ratio changes it to moles of our product, and then we're going to go from moles of our product B to grams, and then we are done. So we just do that twice, easy peasy. Divide by the molar mass is the first step, and hydrogen H2 has a molar mass of 2.02 grams in 1 mole of H2, so grams cancel. Next, we're going to change it from moles of hydrogen to moles of ammonia in H3, using the mole ratio of 2 to 3 up here. Okay, and then moles of hydrogen have canceled. And lastly, I want to change it from moles of ammonia in H3 to grams. And so we have to add up the molar mass of our NH3. That's 14.01 plus 3.03. We get 17.04 grams of NH3 in 1 mole. And let's see what that value is. So we have 5,220 divided by 2.02, okay, equals, divided by 3, the order that we do it in should not matter, equals, and multiplied by 2, and multiplied by 17.04, equals, okay, so we're going to get 29,356 grams, or 29.356 kilograms. Okay, we can write it as either. Since it didn't specify that it wants it in grams or kilograms, leave it in grams. That way you have less of a chance of messing up. Okay, so first we're going to divide by the molar mass of N2. That's 14.01 times 2, 28.02 grams of nitrogen in 1 mole. And then I have, make sure you put your formula there. Moles of N2 need to go on the bottom, and moles of ammonia go on top. Okay, and the ratio here is 1 nitrogen makes 2 ammonias, so 1 to 2. And last but not least, we have to take our 1 mole of NH3 and multiply it by the molar mass, which is still 17.04 grams. And let's see what we get for our nitrogen. Here I have 31,500 divided by 28.02 equals times 2 and times 17.04. Okay, and this one gives me 38,312.63. That's clearly way too many sig figs, but we'll deal with that in a second. Grams of NH3. Okay, so the question said, what is our theoretical yield? I have 2 answers here. The theoretical yield is how much we could make if we used up all of our limiting reactant, and it's always the smaller number. So let's rewrite our answer nice and clear. Theoretical yield equals 29,356 grams. Now we kind of need to worry about significant figures. So I started with 3 sig figs, so I need to end with 3. That is 2 9, and if we're rounding right here, the 5 makes the 3 round up. Add zeros for the placeholders. 29,400 grams of NH3 is our final answer. Okay, last but not least, we're going to go over the for practice 4.4. I'm going to call it FP 4.4. And we have our reaction of iron oxide plus carbon monoxide making iron and carbon dioxide. So they're taking the iron out of the iron oxide. We have our two givens. Let's write those down. 85.8 grams of CO is reacting with 72.3 grams. Sorry. I'm getting ahead of myself here. I missed this 167 grams of Fe2O3. Okay, and the number I was writing down, that is my actual product. So that's what we're going to use at the end to find the percent yield. Okay, so make sure that you read the full question, not like I just did, and work out the process in your head before you get started. Okay, so I'm going to divide by the molar mass of carbon monoxide. That is 12.01 plus 16. So we're going to have 28.01 grams in 1 mole of CO. Now we need to change it from moles of CO to moles of our product that we care about, which is the iron. Okay, they're asking us for the theoretical yield of iron. And so the mole ratio from the balanced equation over here is we get 2 irons. 3 carbon monoxides give us 2 irons. So 2 up here from in front of the iron and 3 down here. Okay, and then lastly, 1 mole of Fe. We need the molar mass of iron up there. I'm going to get to that in a second. Down here, I have grams of Fe2O3 in 1 mole. That's the molar mass here. Okay, I'm going to set these up before I look up some numbers here. And so grams will have canceled as soon as I fill in that number. Moles of Fe2O3, and I'm changing that to moles of Fe. That comes from our balanced equation. So again, I'm making 2 of these, and we're starting with 1 mole of our iron oxide. Okay, and last step is to take moles of iron and change it to grams of iron. So we need to plug in the molar mass. So let's look up the molar mass of iron. $55.85. Okay, and so I still need to add up this one as well. So that is 2 times 55.85 plus 3 oxygens. That's 3 times 16. And let's see what we get. 3 times 16, I think, is 48, but let's make sure. Yes, okay, so that's 48. Let's do 55.85 times 2 plus 48 for a total molar mass of 159.7. That needs to go right here. Okay, did I fill in all of our spots? Yes, we did. So now we just got to do some calculating. All right. So we are going to take my mass of carbon monoxide, 85.8. We're going to multiply it by 2. We're going to multiply it by 55.85. I'm going to hit equals, and we're dividing that by 28.01 equals, and divide by 3 equals. Okay, so up here I get 114. I'm just going to round it there because we had 3 sig figs grams of iron. And down here I get 167 divided by 159.7. equals, and then we have to do the times 2 and times 55.85 equals, oh, that is close. This one is 117 if I round it to 3 sig figs grams. So what is my theoretical yield up here? This number is smaller. So CO is the limiting reactant. Okay, don't be lazy, write it out. I'm a bad example. And the theoretical yield is going to be 114 grams of iron. So here's our first two parts. Okay, the last part, it says find the percent yield. So we actually got 72.3 grams. So let's calculate that percent yield. Equals the actual over the theoretical times 100, and that would be 72.3 divided by 114 times 100. I get 63.4%. So the percent yield is 63.4%, and these are all of the things that the question asked us for right here.